Hi guys. So this next unit is all about the gas phase. So we're going to be looking closely at how particles behave when a substance is in the gas phase. So before we actually get going, I want you to brainstorm a little bit on this slide. I want you to write down everything you already know about the gas phase. I want you to write it down, and this is something that we're going to talk about tomorrow to start class. Okay, so pause, right? And when you come back, we'll talk a little more. Okay, so at this point, you guys have already done the gas law gizmo, and you should have looked a little bit at what pressure means. So let's now go ahead and define pressure. So we can actually define pressure using a formula. Pressure is the amount of force exerted by the particles per unit of area. So when you imagine gas particles inside of a container, this is the easiest way to picture pressure. You want to think, okay, well, how many times are those gas particles colliding or hitting the walls and the lid of the container? And how hard are the gas particles colliding with or hitting the container? So I like to think about the number and force of collisions. So whichever way makes most sense to you is fine. Okay, how do we measure pressure? So we actually have two instruments to measure pressure, and we're going to talk about those in a minute. But we have barometers, and they measure atmospheric pressure, and we have manometers, and that measures pressure of a specific gas sample, and we'll get into those in a minute. What are the units for pressure? So there are a lot of different units, and we're going to talk about those in a minute. But the SI units for pressure is called the Pascal. All right. Molar volume. So that means what's the volume of 1 mole of any gas. So we know that if we have 1 mole of a gas at STP, the volume is going to be 22.4 liters, and that's true for any gas. And we know that from the prior unit. What's important to note here, guys, is that this is only true for STP. So what is STP? STP is standard temperature and standard pressure. Standard temperature and pressure, STP. So for standard temperature, there's actually two values. But in this unit, especially when we do calculations, it's always important that the temperature is in Kelvin. So I'm just going to give you the standard temperature in Kelvin, which is 273. In degrees Celsius, that would be 0 degrees Celsius. But whenever they say standard temperature, you want to think 273 Kelvin. Now, standard pressure, there are many, many, many units for pressure, even though pascals are the SI unit. And part of this chapter is you knowing how to convert from one unit to another. And you're going to have to know these standard pressure numbers to use them as conversion factors. So 101.3 kilopascals is standard pressure. 1 atmosphere is another unit, is standard pressure. 760 millimeters of mercury is another unit for pressure. 760 torr is another unit for pressure. So I have 4 different units for pressure, resulting in 3 different numbers for standard pressure that all represent the same amount of pressure. Okay, so this is something that you guys will have to memorize, these standard numbers. And as we do more practice, you'll start to remember them. It won't be so bad. Okay, So let's get to these instruments that we were talking about. So this is called a barometer. And a barometer measures atmospheric pressure. So we are surrounded by air. And the atmospheric pressure is a measure of the force of the air that's like pushing down on us or pushing against us. And if you can visualize this, when we're at sea level, we have a whole bunch of air on top of us pushing down. So at sea level, air pressure is the highest. As we go up in elevation, the air becomes less and less dense. There's less and less air molecules up there, so air pressure decreases. So how this instrument works, this is actually liquid mercury in a dish, and the container is open on top. So the air is able to push down on that mercury. And this is a tube that's closed at the top. So it's almost as if when you like put your straw inside of a drink and then you cover the top of it with your thumb, and then the liquid stays inside of the straw even when you take it out. That's kind of like what's going on here. So when the air pressure pushes down on the mercury has nowhere to go but to rise up this tube. And the height that it rises measures the air pressure. The bigger this height is, the higher the air pressure. If the air pressure gets lower, it would be pushing down on the mercury with less force, and the level of the mercury in here maybe wouldn't be as high. So we can actually use barometers to predict the weather. The higher the level of mercury, the higher the air pressure. That means we're going to have good weather. Where when the air pressure is low, that means we have bad weather coming in. Okay, so that's a pretty cool instrument. This is a manometer. I'll write it over here. And a manometer measures pressure of a sample of gas. So notice that it looks a little bit different. What we did here was we took a gas, right, and we put it inside of a closed container. It's closed on this end. And then here we have an opening. So this gas that's in here is pushing this way, and the air pressure is pushing this way, and we have these two gases pushing against each other. And whichever one is stronger is going to, this is mercury inside of here. It's going to push the mercury in either direction. So notice how this side is higher than this side here. That means that this gas is pushing with more of a pressure than the air on the outside. Okay, so if it's higher over here, the gas has a bigger pressure than the air pressure. So how we would calculate that, if we wanted to know the pressure of the gas inside, we would have to take atmospheric pressure and add this height to it. All right. There also are diagrams that look like this, where we have our gas. I'm going to be horrible at drawing this. Just do your best, guys. Drawing another manometer. Oh my goodness. It's the worst tube I've ever seen. Where we have a different gas sample, right? But the end is lower than the beginning. So this gas is pushing this way, the air is pushing this way. Clearly, in this example, the air pressure is stronger than the pressure of the gas inside of the sample. So, so to calculate pressure of a gas when the manometer looks like this, when it's lower at the end, we actually do the pressure of the gas equals atmospheric pressure minus the height. okay? Because the gas inside is not as strong as the atmospheric pressure. And when I'm talking about the height, I'm still talking about this difference. But now you're subtracting it, okay? So that's for a specific gas. Okay, so I'm gonna kind of go through this fast, guys, because you looked at this already in your gizmo, and we're gonna spend a lot of time looking at real life examples of this in class. But gas laws means that you have to understand how temperature, volume, pressure, moles, how all of those things affect one another as far as the gas particles go. So the first thing I want to look at is pressure and volume. So these actually have an inverse relationship. This is called Boyle's law. So if you take a container and you make it smaller, your particles are going to hit against the walls of the container more. You're going to be pushing your particles closer together. So by decreasing the volume, you're increasing pressure. When one goes up, the other goes down. So they have an inverse relationship. And a graph would look like this. Okay, that's assuming the temperature of the gas and the number of moles are staying constant. We're looking how two things are related to each other. All right, so some real life examples of that. So you guys can obviously read through these, but the one I like to talk about is the water bubbles. So if you imagine like diving down to the bottom of like a 9-foot pool, like one of those big deep end pools, usually when you go down there, your ears start to hurt, right? You start to feel that high pressure as you're down low. As you come up to the surface, the pressure decreases. So, what happens to volume when pressure decreases? Volume increases. Okay. So, this pressure and volume relationship goes on if you think about your ears popping when you're increasing or decreasing in elevation, whether you're on a plane or you're climbing mountains or going into a tunnel on the train. The bends is about like the gas in your blood when you're scuba diving and you're changing, how deep you are versus how close you are to the surface, or squeezing a balloon. So when you're squeezing a balloon, what you're doing is you're decreasing the volume. So what happens to pressure? Increase it until it pops. So these are just like opposite relationships. They do the opposite things as one another. Charles' law studied how volume and temperature are related to one another. And volume and temperature is a direct relationship. As one goes up, the other goes up. So if temperature increases, volume also increases. Or if temperature decreases, volume decreases. That would look like this. Now, the explanation here is not as simple as you would think. To help you remember this, think about when you make something warmer, what do the particles do? They spread out. So that can help you remember like volume gets bigger as temperature gets bigger. But what's important here is that pressure is staying constant. That means that the number of times the particles hit the walls have to stay the same. So if you increase the temperature, your particles are going to move faster, which means they should be hitting the walls more often. But if the container also gets bigger, even though the particles are moving faster, now they have more space, so they're actually hitting against the walls the same amount. So that would be like a real explanation for why this relationship exists. Okay. Real life examples. So hot air balloons, as we turn on that fire, right? Our gas particles, we spread out, we get less dense, and we start flying. Football left out in the cold. So guys, this is true for any type of ball or like if you think about tires, right? If you go outside in the winter and get in your parents' car, usually on a really cold day, the air pressure thing for their tires is going to light up and say that you have low air pressure. So when it gets colder, the volume gets smaller, or hotter, the volume gets bigger. All right. So Gay-Lussac's law is looking at the relationship between pressure and temperature, and this is another direct relationship where when one goes up, the other goes up, or when one goes down, the other goes down. And our graph would look like this to show that. So this is kind of easy to imagine as well. If I increase the temperature, I'm making my particles move faster. If my container is staying the same size, then my particles moving faster, they're going to hit the container more often and harder. So my pressure is going to go up. Opposite, if I lower the temperature, particles are going to move slower, not hit with as much force, not hit as often, pressure is going to go down, right? So again, you guys can read through these examples. My favorite one is the aerosol container. If you think about your hairspray bottle or your deodorant can, they say not to store in hot places. If it's too hot, the pressure of the can get very high, and if it gets too high, it can actually explode. Okay, so those are some examples of that. Finally, we have Avogadro's law, which studies the relationship between N, which is number of moles, that's the symbol for moles in these problems, and volume. And this is another direct relationship. So there's only one relationship that's not direct. So that should be easy to remember for you guys. If the number of moles goes up, the volume is going to go up. If the number of moles goes down, the volume is going to go down. And this makes sense, guys. If you're pumping more gas into something, that something is going to get bigger. So you can think of blowing up a balloon. You're adding gas particles into the balloon's size is going to grow. If you put air into your tires, the tires are going to get bigger because you're putting more gas particles in there. Okay? So that's nice and easy. That makes sense. Okay, now there are two equations that you have to know regarding gases and these relationships. We're going to talk about one today and save the other one for the next video. So this is called the ideal gas law, and the formula is PV equals nRT. So right here, I gave you what all of those letters stand for, and it's important, guys, that I also gave you the units. So these are the units that everything has to be in before you plug any numbers into this equation. So basically, if you know 4 things about a gas, you can always calculate the other thing about it. Okay, that's what this equation is all about. So R is a new constant that you guys have to know. Whenever you see R in an equation, you want to plug in this 0.0821 numbers and notice its units. ATMs times liters per mole times Kelvin. So in order to cancel out units, everything else in the equation has to have the same units as your constant R. And that's where that comes from. Okay, so again, we're going back to unit conversions. So let's look at this question. 80 liters of deadly chlorine gas has a pressure of 900 millimeters of mercury and a temperature of 20 degrees Celsius. Find the number of molecules. So let's write down all of our values and see what they gave us and see what we have to solve for. All right, so pressure, 900 millimeters of mercury. So that's great that they gave me pressure. Is my pressure in the correct units? No, it's not. Pressure has to be in atmospheres to use this equation. So if you guys scroll back to slide number 2, remember this I told you about down here? These are your conversion factors, guys. 760 millimeters of mercury is the same as 1 ATM. So that's my conversion factor. I want to cancel out millimeters of mercury, and I want to end up with ATMs. So I'm going to put 760 millimeters of mercury on the bottom. What's going on with my pen? And 1 ATM on the top. All right, so let's do this. 900 divided by 760. I get 1.18 ATMs. All right, volume is 80 liters, and I'm supposed to be in liters, so that's good. I don't have to convert anything. N is number of moles. Do they give us number of moles in the question? No, they do not. R is 0.0821. That's a constant. Temperature is in degrees Celsius, which I am not allowed to use. So I have to add 273 to that. To convert Celsius to Kelvin, we add 273 and I get 293 Kelvin. Okay, so now let's go to my equation. PV equals nRT. Pressure is 1.18, volume's 80, and I don't know, 0.0821, 293. So to get x by itself, I want to divide. So 1.18 times 80 is going to be divided by 0.0821 times 293. You guys should put this in your calculator as well. Make sure you're using your parentheses correctly. So I'm getting 3.9 as my number of, we solved for moles. Okay. Now, what's super annoying about this question is that they're not even asking me for moles. They're asking me about number of molecules. So we know how to convert from moles to molecules because we know that in 1 mole, there's always 6.02 times 10 to the 23rd molecules. So last unit and this unit are working together pretty closely. So I'm going to take my answer times 6.02 times 10 to the 23rd, and I get 2.4 times 10 to the 24th molecules. Okay. And guys, they can ask you to solve for anything in this equation. So you're always just going to figure out what you're given, make sure they're in the correct units, and do some algebra. Okay. We will get into the combined gas law in our next video. Here's one last practice question.